Now let's consider a system that is in thermal interaction with a heat reservoir. So we have basically all external parameters fixed so that there is no work being done on the system. And I'm going to call these external parameters x. So this will imply d bar w is 0, and in thermal contact with a heat reservoir, and in this case we will have the temperature is going to be fixed by the heat reservoir for small amounts of heat transferred. So that means in the quasi-static limit, the change in the entropy of the system will be the heat added at constant temperature d bar q divided by T, and since d bar q is the heat capacity with all external parameters fixed, Cx is a function of temperature dt over T. If the system is going to evolve from macro state A to macro state B, so if we have initial macro state A and we have final macro state B for the system, then the entropy difference between these two states will be SB minus SA, the integral from A to B d bar q divided by temperature, which is the integral from A to B, the heat capacity with all external parameters fixed as a function of temperature dt over T. So this is the general form of the entropy change of this system that is in contact with a heat reservoir or thermal reservoir. Now, if we consider a special case, if this temperature range TA to TB for the macro states A and B, we have heat capacity of the system is more or less temperature independent. So basically we can treat it as a constant inside this integral. In that case, what will be the entropy difference between these two states? Sp minus Sa will be Cx comes out of the integral A to B dt over T, and that integral is going to give us natural logarithm of temperature in between states A and B. So this will be Cx natural logarithm Tb minus natural logarithm Ta, which will be Cx natural logarithm Tb over Ta. So basically this type of process is called isothermal process. Oh, just 1 second. So the process where we have the system in contact with a heat reservoir and the small amounts of heat is added with a constant temperature, this is an isothermal process. So we have for all infinitesimal temperature ranges here, temperature is fixed, so we have many isothermal processes performed at temperatures varying in between TA and TB, and that's how we envision the entropy change is occurring in the quasi-static limit. So you will see that if I were to look at the limit temperature of macrostate A goes to 0, that means I'm looking at the entropy of the system in the limit temperature goes to 0. And from the third law of thermodynamics, this entropy is 0 or a small finite value S0 that is given by third law of thermodynamics. So we have, if you look at the entropy change, SB, when SA is equal to 0, will become Cx natural logarithm TB over TA, where TA is going to 0. But since the entropy must be a finite value, we must have, in order to solve this problem, as temperature goes to 0, the heat capacity must go to 0 as well. So this is the general behavior we should observe in all macroscopic systems. So this is a general property of any substance that we are dealing with. Its heat capacity must be decreasing, going to 0 as temperature, absolute temperature goes to 0. So that's basically a remark for us, because we have assumed that for the temperature range of interest, the heat capacity is temperature independent. When the temperature on one side is too low, so this assumption may hold as long as we are far away from absolute 0. If the temperature is too low, the temperature dependence of the heat capacity will become important, and actually it will decrease to 0 as temperature goes to 0, so that the entropy must remain finite. As another remark, for example, we can think of this result for the molar specific heat is equal to 3 over 2R for a monatomic gas. So this result that we have is no longer valid as temperature approaches 0 at very low temperatures, because the ideal gas treated as a non-degenerate gas assumption we have in the canonical distribution calculations, this assumption is broken. So that's the main issue with temperature independent molar specific heat for a monatomic gas. So let's keep these 2 points as a remark for us. Now I want to look at a specific example for entropy calculations, and that is the case of a low temperature ferromagnet. Let's say that I have a system consisting of capital N magnetic atoms, and each of these atoms will have a spin 1/2. And there is a critical temperature for ferromagnets. Below a critical temperature, that we call the Curie temperature, we have ordering of the spins because there is a strong interaction between the spins, the so-called exchange interaction. The interaction between the spins is basically going to force them to align, causes them to align parallel to each other. This is the exchange interaction. This type of ordering is called ferromagnetic ordering. So if you have all of those capital N moments pointing up at the same time, that means the number of accessible states to the system is 1. The corresponding entropy K ln omega is equal to 0. On the other hand, if I have an absolute temperature greater than the Curie temperature, this interaction is gone and the spins are randomly oriented. So I have full randomness, randomly oriented up and down with no preference for up or down directions. Then for this limit I will have the number of accessible states, because for each spin I have up and down 2. For n spins it will be 2 to the power capital N, and the corresponding entropy will be K natural logarithm 2 to the power N, so it will be capital N K natural logarithm 2. So if you look at the entropy change from 0 temperature to infinite temperature, regardless of what the temperature dependence of the heat capacity is, the answer is given by the entropy for absolute temperature much greater than Tc minus entropy for temperature much less than Tc, and that is equal to Nk natural logarithm 2. So this is irrespective of C of t or the type of interaction, as long as at a low enough temperature I have one accessible state, and at a high enough temperature I have completely random orientation, this argument will hold. Actually the ferromagnet turns into a paramagnet at high enough temperatures. That is a phase transition, and in this phase transition we have a change, a sudden change in the entropy of the system, which is what we see in this example. So let's recap. When all the external parameters of a system are fixed, there is no work done on the system. And if this system is in thermal contact with a heat reservoir, which keeps the temperature fixed for small amounts of heat transfer, that's called isothermal process. If we go from an initial macro state to a final macro state using a quasi-static process, if we do it slowly, basically you can think of this process as the system has been in thermal contact with successively higher temperature heat reservoirs. So starting at temperature Ta, it's in contact with a heat reservoir at temperature Ta, and then we go to one at Ta plus epsilon, Ta plus 2 epsilon, etc., until we reach temperature Tb. So many heat reservoirs with slightly higher temperatures forming thermal contacts with the system. So that's the way we can think about it. And taking into account the temperature dependence of the heat capacity, the entropy change would be integral from A to B C dt over T. If for the temperature range of interest the heat capacity seems temperature independent, we can formulate the entropy change as Cx for external parameters fixed, natural logarithm Tb over Ta, which shows us that as Ta goes to 0, entropy must go to 0 or S0, by the third law of thermodynamics. So when you set SA equals to 0, that means SB must be equal to Cx natural logarithm TB over TA, where TA goes to 0. For SB to be finite, since TB is already finite, Cx also must be going to 0. So 0 over, so you will have 0 natural logarithm finite number divided by 0. So this is going to give you, that's the only way you can get a finite answer from this formulation. And that's a general property of any substance. If the heat capacity, if the temperature is too low, the heat capacity must be decreasing. So heat capacity in general must be considered as a temperature dependent quantity. If you go to our treatment of the monatomic ideal gas using the canonical distribution, where we assume that we have a non-degenerate gas, we obtained 3 over 2R, a temperature-independent molar specific heat, and this non-degenerate gas assumption is broken at low temperatures. And then we have looked at a specific example, a low temperature ferromagnet which has capital N magnetic atoms with spins 1/2. Below a critical temperature called the Curie temperature, there is a phase transition. All of those moments line up and giving you one accessible state with corresponding entropy 0. For the temperature greater than the Curie temperature, the spins get randomly oriented. The phase transition occurs from ferromagnetic ordering to paramagnet. And then we will have number of accessible states 2 to the power n. So you can see that the entropy change is nk natural logarithm 2, irrespective of temperature dependence of the heat capacity or the type of interaction that is involved between the